Hello everyone, in today's video we're going to be covering buffers, and so according to our checklist up here we're going to be going over what is a buffer, and then we're going to relate the Henderson-Hasselbalch equation, which is an equation that we can use to solve for the pH of a buffer without going through the entire steps of the equilibrium acid ionization reaction. And then if we have enough time by the end of it, we'll look at an example, and if not, we will make another video um, doing the example. So what exactly is a buffer? Well, a buffer is a solution that can resist changes in pH. So if I add a strong acid to a buffer solution, the pH will remain relatively stable. And so what I mean by that is if I take a strong acid, let's say hydrochloric acid, for example, and add it to water, the pH is going to significantly decrease. It's going to become lower. So maybe from a pH of 7, which is the pure pH of water, to a pH of maybe 4. And so what happens when we have a buffer solution is we can add that hydrochloric acid in, but the pH will remain relatively stable, only varying by maybe 0.1 or 0.2 units of pH. And so before we get into anything else, I want to look at how can we make a buffer? So how to make a buffer. How to make a buffer. Well, there are four main ways to make a buffer, and to look at that, we can say that, well, a buffer is made up of a conjugate pair. So conjugate pair, and what I mean by that, and I'm assuming that you've already gone over acid-base equilibrium, as a conjugate pair is a weak acid in its conjugate base, or a weak base in its conjugate acid. So when we look at things, we can say, well, how are we going to make a buffer? We can combine a weak acid with its conjugate base salt. And similarly, we can do the same thing. We can combine a weak base with its conjugate acid salt. Its conjugate acid salt. And so for this method, it's basically like taking a beaker of, let's say we have a beaker of sodium acetate and a beaker of acetic acid, and combine them and we make a buffer that way. Two other ways, and they're very similar in terms of how we do them, is we're going to look at partially neutralizing. Partially neutralize a weak acid with a strong base, or we can partially neutralize I'm sure you can guess it, a weak base with a strong acid. And when we're going to look at this more closely, we're going to look at this using a method called titration. And so I'm sure you already know about titration. You may have done a redox titration earlier in your chemistry class. So now we're going to be looking at a acid-base titration. We'll cover more in depth about acid-base titrations and calculations using partial neutralizations in another video. And so now what I want to look at is the maybe an acid ionization equation. So we can look at this and we can say, well, we have HA, and we're going to say that this is our weak acid. We're going to add water. We know that this is a liquid because we're an aqueous solution. And because we have a weak acid, this is going to be an equilibrium reaction, so that's going to form the hydronium ion and then the conjugate base. And so now I kind of want to go in and explain why buffers work in the way that they do. And also let's say we're going to go up here and we're going to add maybe some NaA. And because we know that sodium salts dissociate completely, we have Na plus and A minus. And so what happens here? Well, if we have just the regular acid and we add a salt to it, we're going to increase the amount of the conjugate base in here. So if we increase the amount of conjugate base, well, according to the Le Chatelier's principle, that's going to actually shift the equilibrium reaction to the left to make more of the acid. And similarly, if we add more acid, get a different color here. If we have more acid, well, that's going to shift the equilibrium reaction towards the right. It would make that. So basically what's happening here is that we're having the shifting of this reaction in a buffer, and it will keep the pH pretty consistent because the base is going to pull in some hydronium, and so that's kind of where we're looking at in terms of pH. And so before we keep going on to the derivation of the Henderson-Hasselbalch equation, I want to look at, why do we care about buffers? I think it's very important to look at, we can sit here and learn about buffers all we want and properties of buffers, but why do we care about buffers? And well, buffers exist in nature and they allow for sustainable life. So for example, blood contains a buffer, and that buffer is carbonic acid, which is H2CO3, and the hydrogen carbonate ion, which is HCO3 minus, which we can see that is the conjugate base of carbonic acid. This is especially important for certain biological processes. Enzymes can only function in specific pH ranges before they start to break down. Also, the solubility of oxygen is very important when looking at buffers. The solubility of oxygen changes with respect to pH. So if you have more saturated oxygen in your blood or not enough saturated oxygen in your blood, well, that could eventually become fatal. Another example where we can see solubility of oxygen come into play with pH is in specific bodies of water, such as lakes and rivers. Some of these lakes and rivers will have natural buffers that resist these changes in pH. So if there's a significant change in pH, then if there's a significant change in pH, then life in that body of water will cease to exist because there won't be enough oxygen in the water. So those natural pH buffers are really, really useful when we're thinking of things like acid rain, for example. And so now that we've discussed kind of why we like buffers, let's derive the Henderson-Hasselbalch equation. And so before we go on, let's write just the Ka expression, which is actually what we will use that to derive the formula. So if we have a Ka expression up here, we have Ka, and this is a Ka because it's an acid. So Ka is equal to the concentration of the hydronium ion times the concentration of the base all over the concentration of the acid. Well, I want to point out something that's going to come up later in the Henderson-Hasselbalch equation, which we're actually, in this equation, we're going to be able to use initial concentrations of the buffer. And I'll tell you why, because when we have this, we're going to end up with some concentration, and then we're going to have plus x, and then that'll be times x, and then we'll have some concentration in the denominator, and that'll be minus x. And so actually what we'll be able to do is we'll be able to neglect this plus x and neglect this minus x. We can neglect the plus or minus x because the concentration, these two concentrations are going to be 100 times greater than the Ka. Well, why do we know that? The Ka for a weak acid is something we're looking at the -5 to -10, and so we're usually going to be looking at concentrations that are maybe 0.1 molar, 0.2 molar, and so we will have the concentration always being 100 times the Ka. So whenever we're actually using the Henderson-Hasselbalch equation, we can actually use initial concentrations, which will be very useful. So now let's actually derive it. So I want to sit here and let's rewrite the Ka expression because this is what we're going to derive it from. So we have Ka is equal to the concentration of the hydronium ion. And we can also abbreviate this as H plus, but it's actually more accurate, right? As the hydronium ion times the base all over the concentration of the acid. Well, if we multiply, we can say that if we multiply by HA all over the concentration of A minus, and we have to do that on both sides, so times HA over A minus, Well, we see here that this cancels with that, and that cancels with this. So I'm just going to write this on the left side now. So now we have the hydronium ion is equal to the Ka times the concentration of the acid over the concentration of the base. And so now what happens if we take the negative log of both sides? So if we take the negative log of both sides, and I've written this so many times and I never leave myself enough room, so if we take the negative log of both sides, well, what is the negative log of the hydronium ion? Well, we know that to be pH. So we know that this is pH. So we can say that pH is equal to the negative log of the Ka minus the log of the concentration of the acid over the concentration of the base. Well, what is the negative log of the Ka? Well, we know that the negative log of the hydronium ion is the pH, so that the negative log of the Ka is actually going to be the pKa. So we can say that pH is equal to the pKa, and then let's look at this. So if we know our properties of logarithms, we can say that out here is a coefficient of -1. So if we write like just a -1 right there, excuse me, if we have a -1, we can actually take this -1 and put it in as an exponent for the logarithm. And so we know that based on our properties of logarithms, and so if you actually need to review those properties of logarithms, I really encourage you to do so, because logarithms seem to be so important when we're dealing with acids. So now that we know that we can put that exponent there, well, now this turns into plus the log of the concentration of the base over the concentration of the acid. And so we can define this to be the Henderson-Hasselbalch equation. Just box this in here. And so this is the Henderson-Hasselbalch equation. And so now if we're given a problem, we can say, well, we want to make a buffer that is 0.1 molar sodium acetate, NaA. We're just going to abbreviate that to be NaA, and maybe acetic acid. We can actually use the initial concentrations, because we're actually neglecting X in here because it's so small, because the Ka is going to be so small. And so that is the Henderson-Hasselbalch equation, and I've actually run out of time here. So in the next episode, we are going to look at a couple examples. So we're going to look at an example where we make a buffer using a specific volume of an acid and a specific volume of its conjugate base salt. And then we're going to see what happens to the pH whenever we add hydrochloric acid, or just a strong acid in general, to the buffer. So thanks for joining me. I hope you learned something, and I will see you in the next video.